In this video, we will learn about light being reflected through different lenses as well as the variables involved. To begin, there are three different types of light. We have waves that you see, rays, which is reflected light, and photons, which are particles of light. Now, when light passes through a lens, it is refracted. Refraction is defined as the fact or phenomenon of light being deflected after passing from one medium to another. Two different mediums could be air to water, air to glass, glass to air. So when we think of lenses, we have two different types. We have a converging lens and a diverging lens. Converging lenses are described as the light enters rays into a more dense lens material. So as we see here, the light coming into the dense material because the thickest part of the lens is the center. They refract towards the normal, which is also known as the focal plane, and as they exit into the less dense air, they refract away from the normal, which we see after the focal plane. Now, when these three rays come in and are converged, they all meet up at a focal point. A converging lens always has a positive focal point because it's always in front of the lens, and the distance is known as the focal length. Diverging lenses, however, are concave. They take light from the focal length or from the focal point on the focal plane, which is also the normal, and they take the rays and diverge it out. So it's taking the rays into a less dense material in the center where it's skinny and diverging the light away from normal. The distance from the focal point to the center again is F, which is your focal length. So now that we know F is our focal length, we also need to identify other important variables. So in the first equation, we have the reciprocal focal length is equal to 1 over S, which is object distance, plus 1 over S prime, which is image distance. The second equation in the box deals with magnification. Magnification is equal to H prime over H, where H is the object's height and H prime is the image height. Now you'll notice that the primes are for the images and the S and H are for the objects. So why are these variables important? What do they tell us? If you look on the left, you'll see if we have a negative magnification, it will tell us if the image is upright or inverted. And if our magnification value is larger than 1, it's enlarged, smaller than 1, the image is diminished. The S object distance and F focal length are important to tell us if the image is real or virtual. So a way to draw all of these rays and these variables interacting together is a ray diagram. When we use a diverging lens, we draw it at the origin, and we create two focal points because in a thinner lens, it takes rays from the left and right. That is why we see two focal lengths. So you go from the center to create your focal point created by your focal lengths. Now when we look at this diagram in specific, we can count from here all the way to the center is S, the object's distance. From here down to the axis would be S prime, or H prime, H, the object's height. If we were to look from here to here, that would give us S prime, and if we were to look to here to the axis again, that would give us H prime. Now, how do we draw these rays? So when we first draw a diverging lens and we find S, the distance of our object, we can draw three different rays. Of course, there are infinite amount of rays that pass through lenses at times, but we will focus on three important ones. The first ray will run parallel to the center and then reflect through the focal point. So it'll reflect upward, but if we draw its reflection, it's going back down through this focal point. For ray 2, we see that it passes through the focal point and emerges parallel. So we draw emerging through the focal point. If it were to continue on this black dotted line and go through the focal point, but then it turns parallel. So we also draw this ray's reflection as you see in the dotted blue lines. The last ray is drawn straight down through the center of the diverging lens. Where all three of these meet, the two reflected rays, is where the image will sit. Diverging lenses will produce virtual images. So now let's try a problem. This says that a diverging mirror has a focal length of 12 centimeters. But remember, focal lengths are always negative for diverging lenses. It wants us to locate the image for an object distance of 20 centimeters. So if we were to use our first equation and plug in our values and rearrange, we would find our S prime value, which is negative 7.5 centimeters. Part B asks us to find the magnification. So if we were to use our equation, we would use the second part of this equation because we don't have the heights for either the image or the object. So negative S prime over S, and we need to plug in our values to find M, gives us positive 0.375. Part C asks us to look at the values obtained and determine the image. So we know that magnitude is positive and that it is also greater than 1, or less than 1, excuse me. Therefore, we know that the image is upright and diminished. The problem also asks us to determine if the image is real or virtual. Now in the problem we are given positive 20 centimeters. However, if we look at the ray diagram from before, we know that the image is actually behind the lens. Therefore, when we take into account values, we will say negative 20 for object S, object distance S, is less than negative 12 focal length F. Therefore, we know that the image is virtual. Lastly, we are asked to draw the ray diagram that supports our answers. So in this diagram, we have the diverging mirror drawn and two focal points set. We know that the focal points are each at negative 12 and positive 12. The image distance is negative 20. And from there we can draw our three rays. So the first ray we want to draw goes from the top of the object and then to the center and then continues outward through the focal point. So if we were to draw the reflection of this line, we would draw it dashed through the focal point. Ray 2 is drawn directly from the top to the center and then carries on parallel to the axis. Again, if we were to draw the reflection, we would draw it like this. And lastly, our third ray will travel straight through from the top through the center. And where these three lines meet up, we know will be the S prime, which we found to be negative 7.5, which makes sense because it should be in front of the focal point.